So yesterday, we were going over Newton's second law. Okay, we said that Newton's second law relates net force to mass and acceleration, but it can also be calculated by the vector sum of all forces. Okay, and that we would end up likely using both of those anytime we encounter a Newton's second law problem. Okay, so we know that F net equals mass times acceleration, but this formula is true for any individual force as well. Okay, I can calculate an individual force by multiplying the mass by the acceleration that force would produce when acting on that mass. Okay, case in point, or the most common one that we calculate, is this one, the force of gravity. Okay, now the force of gravity is mass times which acceleration? Right, 9.81, which is such a common acceleration that we use that we actually abbreviated little g. You've probably seen that on the back of your formula sheet. Okay, little g is 9.81 meters per second squared. All right, so we can calculate the force of gravity with that formula. Okay, and so what we end up having lots of times, okay, in like a Newton's second law problem, is that F net equals like an applied force plus force of gravity plus some other forces, and we end up adding them all together. Okay, well, sometimes we have to calculate those individual forces. Okay, and we calculate gravity in particular in this way. All right. Now the reason I bring that up is because using that formula, Fg equals m times g, is crucial for solving a very common type of Newton's second law problem. And that is the elevator question. Okay. Now, we call it an elevator question because most of the time the context is an elevator. But any object being moved vertically, that is straight up and down, is technically an elevator. Okay. Me throwing this marker up in the air, that's an elevator. Okay, while it's in contact with my hand, there's a force acting on it upwards and a force acting on it downwards. Okay, it's an elevator. Okay, if I'm using like a hoist, like a cable or a rope operated hoist, okay, that's attached to something heavy and I'm pulling it over a pulley, it's still an elevator. Okay, I'm using it to vertically move something. I'm opposing the force of gravity. So any type of question where gravity is being directly opposed by an upward force is technically an elevator. Okay? Most of the time the context is actually an elevator. Right? But occasionally it can be something thrown into the air or lifted. All right, so in this particular question, I'm going to have you guys copy this one down because this is your first example of an elevator question. Okay? We need to look at how elevator questions are dealt with. Let's give you a minute to get a copy. Okay. So in this question, they're telling us that the combined mass of the person and the elevator is 600 kilograms. Okay? So they've kind of drawn a free body diagram for us here on the right. Okay? It's much nicer than my free body diagrams, which are a box with arrows coming out of them. Theirs is a fancy box with a picture of a person inside with arrows coming out of it. Okay? So it's still kind of a free body diagram minus this important piece of information. The mass is 600 kilograms. Okay? That's something that's supposed to go inside that box. Now it says, calculate the acceleration of the person. Is the acceleration of the person the same as the person and the elevator? It better be, because if it's not, the person's flying around inside the elevator. Okay? So yes, when the elevator is doing anything, the acceleration of the person inside is the same as the elevator. Okay? Now, there is kind of a moment when an elevator first gets moving that's not necessarily true. Okay? And you can feel that. If you've ever ridden in an elevator, when an elevator first starts to descend, there's this sensation of the floor falling away from you. Okay? That's an inertia thing. Okay? Your inertia is to stay put, but the elevator is actually being pulled. Okay, in one direction or the other. All right, so if the elevator is being lowered, the floor doesn't push on your feet as hard as it does when the elevator is stationary, because it's accelerating downwards. Okay, not at 9.81, okay, because then you don't need an elevator. Okay? If it's going to accelerate downwards at 9.81, it's no different than jumping out the thing. Okay? So you don't have to worry about an elevator doing that. Okay? But it does accelerate downwards. In order for it to accelerate downwards, the floor can't push on you as hard as it would if you were standing on it stationary. Similarly, when an elevator starts to accelerate upwards, it pushes on your feet harder than it does when it's stationary in order to cause you to go up. Okay? So you feel a little bit heavier when an elevator first starts to move. An elevator does not accelerate through its entire motion. It accelerates for the first couple of seconds, and that's it. Okay? Most elevators only accelerate for maybe a second. Okay? And then they move at a constant velocity. When the elevator is moving at a constant velocity, do you feel normal, heavier, or lighter? Normal. Okay? It's moving at a constant velocity. What's the net force? 0. So you feel perfectly normal. Okay? When the elevator first starts to accelerate upwards, you feel a little heavier. When the elevator first starts to accelerate downwards, you feel a little bit lighter. In fact, if you had a scale in the elevator with you, it would fluctuate. Okay? If you were standing on a scale and the elevator started to descend, it would read a lighter number. In case you ever want to do that. You're only lying to yourself, but I mean, you wanted to try that. Okay? And similarly, when the elevator starts to move upwards, the scale would read heavier. Okay? Because there's more force pushing on your feet to accelerate you up, or less to accelerate you down. Okay? Everybody okay with that idea? All right. So the reason for that is there's an interaction of two forces anytime an elevator moves. Okay? So in order to make an elevator move, a motor is always pulling up. Now that may seem weird. Okay? Even when an elevator is being lowered, there is still an upward force. Okay? Think about if you wanted to lower something off the roof of your house with a rope. Okay? Lower it, not drop it. Okay? Because you can push it off the edge and it'll get to the ground. It's got to be in pieces though. Okay? If you want to lower it, you put a rope on it, and which way do you pull the rope? Towards you, up. Okay? You lower something by pulling up. But you don't pull up as hard as gravity pulls down. Okay? It moves downwards. There's a net force downwards, so it goes down. Okay? If you wanted to lift something onto your roof from the ground, you still pull up. Okay? There's always an upward force. If there isn't, then you're just falling. Okay? And the net force would be gravity, down, 9.81 meters per second squared. All right, so in this particular question, they're telling us, here's the mass of the elevator. It's being pulled downwards by gravity. And upwards by the cable, which is an electric motor. Okay, but we'll just say it's tension in the cable. Okay, the question also tells us that this tensional force is 6,500 newtons. Okay, it says the elevator cable exerts a force of 6.5 times 10 to the 3 newtons up on the elevator. So this is 6,500 newtons. Okay. Now, gravity is pulling down. I need to calculate how big gravity is so that I can do the vector sum of all forces, which I need to do in order to find the acceleration of the elevator. Just like the questions we did yesterday with the friction acting backwards and the bobsled people pushing forwards and stuff like that. It's just now it's up and down. Okay, so how do I calculate this force of gravity here? Take the mass, I multiply by 9.81. Okay, I use the formula for the force of gravity. This calculates the weight of the elevator, okay, in newtons. So I take my 600, multiply by 9.81, okay, and I get that this is 5,886 newtons. Okay, so I have a force of 6,500 newtons up, 5,886 newtons down. Which way is the elevator accelerating? Up. Why? Right, the force up is bigger than the force down. In other words, when I do this calculation, F net is the sum of all forces. That's going to be tension plus the force of gravity, I'm going to have 6,500 plus negative 5,886, or minus 5,886, right? It's the vector sum of all the forces. Okay? When I do that, I get that my net force is positive 614 newtons, or 614 newtons up. Okay? If there's a net force, the object is going to accelerate in that direction. Okay. Can I calculate the acceleration of the elevator? Yeah. Now I have net force, and they told me it has a mass of 600 kilograms. So the acceleration of the elevator is going to be 614 newtons up divided by 600 kilograms. That's 1.02, I think, right? Meters per second squared up. Is that very much? 1 meter per second? Not much of an acceleration, but you'd notice it. You'd feel the floor pushing on your feet, okay? A little harder than normal, okay? About 10%. So you feel about 10% heavier in that situation. All right, so the elevator questions make sense? Okay? You got a force up, maybe you have more than one force up, you got a force down, okay? And that force down is always going to be, and what force in particular is going to be gravity, right? It's the weight, okay? Force down is always your weight. Okay. So now, looking at question number 1, so same person, same elevator, okay? So the mass is still 600 kilograms, okay? Now the cable exerts a force of 5.2 times 10 to the 3 newtons up. Calculate the acceleration of the elevator now. Okay, don't worry about question number 2 because we got to go through that one together. Okay. So for question number 1, okay, first thing again is we draw our free body diagram. Okay, so we got our 600 kilogram elevator and occupant. Okay, we've got the force upward, which is the tension in the cable, which they're telling us is 5,200 newtons. Okay, we have the force downwards, which is the force of gravity. Okay, and we calculate force of gravity by going m times g. That's going to be 600 times 9.81, which is 5,886 newtons. Right? So now I know those two forces. Right? I know now all of the forces. So can I calculate the net force? Yes. Okay. Remember that net force is the vector sum of all forces. That would be tension plus the force of gravity. Okay, and in this case, that's going to mean m times a equals 5,200 newtons plus negative 5,886 newtons. Okay, which means my net force, m times a, equals 686 newtons down. All right, so now the elevator is being lowered. My net force is down. Okay, the cable still pulls up in order to do that. It just doesn't pull as hard as gravity, so that there's a net force in a downward direction. Okay, so now I can calculate the acceleration by going 600. Whoop, I don't know why I put a point there. 686 newtons down divided by the mass of the elevator, 600. Okay, that's going to give me my acceleration, which is 1.14 meters per second squared down. No. In this one, they give you up. So you have to use up. All right. Questions on that one? Okay. Now, number 2 is still an elevator question, but it sets up differently because they want us to find the mass. Okay? And this can be a little bit tricky because I have to have mass to calculate the force of gravity, and I don't have it. Okay? So I have to look at this one a little bit differently. Okay? So in question number 2, I have an electric chain hoist. So kind of like what I was saying, if I want to lift something off the ground and I use like a pulley or a hoist, okay, I'm lifting it directly up. It's still an elevator. Okay? It exerts a force of 2.85 times 10 to the 3 newtons up on an engine to remove it from a car. Okay? The acceleration of the engine is 1.5 meters per second squared up. What's the mass of the engine? Okay. So I need to draw my free body diagram. I have no idea what the mass is. That's what I'm being asked to find. So it makes it a little difficult. One of the key parts of my free body diagram is actually missing here, right? I do know this upward force, okay, and it is 2,850 newtons, okay? What other forces are acting on the engine? Gravity. Can I calculate the force of gravity? I don't have mass. Force of gravity is mass times gravity, so I can't calculate the force of gravity. But here's what I can do. Okay? On all the previous questions, I set them up like this. I said net force equals the vector sum of all forces. So in this case, that is the force of the hoist plus the force of gravity. Okay? That's what the vector sum of all forces for this question would look like. Even though I don't know what those forces are, that's what it looks like. Okay? Like I don't know what they are numerically. Okay? I know what they are in terms of what they are. I just don't know what they are numerically. Okay. The other way to calculate F net is this. Mass times acceleration. Okay? And if you remember, I said you can calculate any individual force by multiplying the mass by the acceleration that force would produce. So that's what I want to do next, is I want to rewrite this force formula as a mass and acceleration formula. Okay, so I'm going to write it mass times acceleration, and I'm going to say net here because that's the net or overall acceleration, and I actually got that number. Okay, they told me the net acceleration here is 1.5 meters per second squared. Okay, so I'm just going to write that down as a given. Okay, so that's going to equal mass times the acceleration of the hoist. I don't know what that number is. That's okay. Okay, plus mass times gravity. Okay, now that I have it set up that way, every one of those terms contains what? Mass. Every term is being multiplied by mass. What can I do with it? Yeah, I can cancel it off. Now, probably a lot of you are going, there, you've lost your mind. You're supposed to be finding that, not canceling it. Trust me, I'm getting there. Okay, I'm going to get there, right? Here's why I want to cancel off the masses. If I take these masses out, now what I'm saying is net acceleration is the vector sum of all accelerations. Also true. Okay? So my net acceleration, which I know the value of, equals the acceleration of the hoist plus g. Do I know what g is? Yes. Okay. Can I find something I didn't have before now? I can. Okay. I can find the acceleration the hoist would produce were it working in isolation. Okay. That is, what acceleration could the hoist produce if there was no other forces working against it? How is that going to help me? The force of the hoist, which they gave me, is equal to mass times the acceleration of the hoist. So if I can find the acceleration of the hoist, I can find the mass of the engine. We call this the differential acceleration method. It sounds really complex, but basically it just means take the forces out and just work with the accelerations instead. The same is true. They're all being multiplied by the same mass. Okay? So I'm going to solve for the acceleration of the hoist by subtracting g. Right? So I'm going to have the net acceleration minus the acceleration due to gravity equals the acceleration of the hoist. Now, I have to be careful here. Vectors matter. Right? So I'm going to have 1.5, which is positive. That's the acceleration, the net acceleration, minus negative 9.81. That equals the acceleration of the hoist. So if the hoist were working in zero gravity, I'm now going to calculate the acceleration it could produce, which should be bigger than gravity after all. Right? If it wasn't bigger than gravity, the engine wouldn't be moving upwards. All right, so I'm going to have, oh, sorry guys, I didn't fire up my calculator earlier. That's not what I want. Oh, no.
Just full screen.
Okay. I hate that. Okay. Windows, I don't like that. Okay, 1.5 minus negative 9.81. All right, so the acceleration the hoist could produce is 11.31 meters per second squared up. Okay, if there was no gravity, that's what the engine would be doing. Okay, accelerating upwards at 11.31 meters per second squared. All right, so now that I have the acceleration of the hoist, I'm going to go back to this. Force of the hoist, which I know, equals mass times the acceleration of the hoist, which I now know. So now I can calculate the mass of the engine. Right? So I'm going to isolate the mass of the engine. Okay? I'm going to have force of the hoist minus the acceleration of, or divided, sorry, by the acceleration of the hoist equals m. So that's going to be 2,850 newtons divided by 11.31. Right? That's going to get us 252 kilograms. Right? It is very rare that you run into a differential acceleration method question. Most of the time, you can just use the forces. But every once in a while, they throw one at you where they don't give you the mass, and this is what you have to do. Okay, everybody all right with that one? Alright, there's a differential acceleration method question. Now it's a skydiver instead of an engine. Okay, so see if you can figure out the mass of the skydiver. Basically the same method we just used. See if you can apply it to this question. Okay, so for this one here, okay, we still have the same forces. We've got gravity pulling down. Obviously gravity is bigger, okay, because the person is falling. Okay, and we've got the force of air resistance, or friction, acting upwards on the skydiver. We know that this force of friction is 250 newtons, right? And we know that their overall acceleration, that is their net acceleration, is 5.96 meters per second squared in a downward direction. Okay? All right, the other force is obviously the force of gravity. We can't calculate that yet. Our net force formula looks like this. F net equals the force of friction plus the force of gravity. Expanded, that's this. Mass times the net acceleration equals mass times the acceleration due to friction plus mass times gravity. Okay, that's our net force formula. We don't have mass, but it's okay. It's in every term. So I'm going to cancel it out. I know what g is. I know what the net acceleration is, so I can isolate the acceleration that friction is producing. Okay? Now, common sense-wise, if I'm accelerating downwards at 5.96 and I should be accelerating downwards at 9.81, the difference is the acceleration produced by friction in an upward direction. Everyone okay with that logic? Okay, so that's what we're doing here. The acceleration due to friction is the net acceleration minus the acceleration due to gravity. Right, so that looks like this. Negative 5.96 minus negative 9.81. They're both down. And I'm subtracting them. So that's going to give me the acceleration that that force of friction of 250 newtons is producing. So negative 5.96 minus negative 9.81. All right, so friction is producing an acceleration of 3.85 meters per second squared up. All right, now that I know that, now I can go back to this. The force of friction equals mass times the acceleration due to friction. I know the force of friction, 250. I know the acceleration, 3.85. Now I can solve for m. So m will equal 250 divided by 3.85. All right, so we're looking at the person's mass being 65 kilograms.
Explain again why it's -5.96.
Because it's down. I made down negative. Yeah.
That makes sense.
Yeah. Yeah, we should have 3, so 65.0 or no, 64.9. 64.9 kilograms. Okay. All right. Everybody okay with that one? All right, so these are all still using the same idea that we were talking about yesterday. Net force is the vector sum of all forces. Okay? Yes, we can isolate that down if we don't have mass. We would use this method. It doesn't come up very often, but at least we kind of know how it works at this point. Okay? So what we're going to start doing now is looking at more and more complex situations in which Newton's second law applies. Okay? All right. Okay, give number 1 a try here. I'm going to make it a little bit bigger so you can read it. Okay, and the answer that's 5.2. Okay, just so you have it here, it's all right. Give number 1 a try. Okay, still an elevator question. The bungee jumper is still an elevator. Okay, there's gravity pulling downwards and hopefully the bungee cord pulling upwards. Okay, so let's look at the bungee jumper question here. So we have a bungee jumper with a mass of 55 kilograms. Okay, and fastens one end of the cord made of elastic material to her ankle and the other end to the bridge. That is good. Only attaching it to one of those is bad. Okay, so she's going to have this cord that is going to pull upwards on her when it becomes taut. Okay, so obviously when she's in free fall, it's just slack and it's not doing anything. Okay, so there's a force of gravity, obviously, pulling down on her, which I can calculate because I have her mass and I know what G is. Okay, so really quickly here, we're going to calculate that force of gravity, 55 times 9.81. So 539.55 newtons. Okay. We want to calculate her acceleration at the instant the cord exerts an elastic force of 825 newtons up. All right, so when the cord becomes taut, it starts pulling upwards. And actually, the further she falls after it's taut, the harder it's going to pull. But at this instant, it's 825 newtons. Which way is she accelerating? Up. She's still falling down, but she's accelerating up, which is good because that means she will eventually what? Stop, and not because she hits the ground, hopefully. Okay, but because the bungee cord is slowing her fall. Okay, it's making her accelerate upwards and slowing her fall. All right, so right now, if I want to calculate her acceleration, okay, that's part of F net. It equals m times a. But it also equals the vector sum of all forces, which would be, okay, the force of the elastic plus the force of gravity. Okay? It's still an elevator. Right? It's still two directly opposed forces. All right, so now, okay, I want to calculate her acceleration. So mass times acceleration will equal 825 plus negative 539.55 newtons. So 825 minus our answer there. All right, so our net force is 285.45 newtons up. That equals M times A. So how do I get A? Right, the net force, 285, divided by the mass. So I divide both sides by M, 55, and I'm going to get her acceleration. All right, so her acceleration is 5.19 or 5, they have 5.2. I don't know why they have 55 kilograms, 2 sig digs there. So 5.2 meters per second squared up. Okay, that's her acceleration. Okay, everybody all right with that? Okay, now, from a less calculating and more understanding kind of viewpoint, during the bungee jump, the velocity of the 55 kilogram woman at the lowest point is 0. Okay? It's exactly the opposite of what would happen if you jumped into the air. At your highest point, your velocity would be 0. Okay? This is the opposite. You're falling but being pulled upwards. Okay? So at her lowest point, her velocity is 0. That's the point where she changes direction from going down to going back up again. Okay? If you've ever seen somebody bungee jump, that's what happens. They fall, the cord stretches, and then shoots them back up in the air. And you actually get to oscillate for a little while, okay, before they lower you to the ground or pull you back up, whichever they do. Okay? So compare the direction of her acceleration at the lowest point of the jump to the part of the jump where she is accelerating due to gravity. At the lowest point of her jump, okay, where the cord is stretched the most, which way is she accelerating? Up. The cord is pulling up its maximum amount there. That's where her maximum acceleration occurs, is at the point where the cord is stretched the most. Okay? Whereas when she's falling, like just pure free fall, her acceleration is downwards. Okay. All right. I don't know why they asked that twice. It's the same thing. Okay. Now, what's coming up next here is what we call system questions. I'm going to give you about a 3 or 4 minute break here, and then we're going to go into system questions, which involve 2 or more masses in a system. Okay, so I'll give you about 4 minutes, and then we'll get back to this. So let's say at exactly 11. All right, so this is the start of what we call system problems. Okay, systems consist of 2 or more masses. Here's the thing you need to know about any system. It's the most important thing there is. In a system, all parts accelerate at the same rate. Okay? If you look at this system here, where I have a 10 kilogram mass being pulled directly by the hand, then attached to a 20 kilogram mass behind it, it's impossible for those masses to accelerate at different rates. The only way for that to happen is if either the 20 kilogram mass overtakes the 10 kilogram mass, which I can't imagine in this situation how that would happen, or the rope breaks. Okay? As long as they're attached, they have to accelerate at the same rate. If that's not true, then semi-trailers become really dangerous. Not that they're not kind of dangerous already, they're really big. Okay? But if they could have their parts accelerate at different rates, that's bad. Okay? In fact, it does happen sometimes. It's called jackknifing. Okay? It's when the trailer tries to pass the truck. It happens if it gets really icy. The truck slams on the brakes, but Newton's first law kicks in. There's not enough friction to stop the trailer. The truck starts to stop, but the trailer just keeps on going, and it tries to swing around and pass the truck, causing it to close like a jackknife. Okay? That's Newton's first law. Okay? That would be the only situation in which the acceleration of the two parts would be different. Okay? In this situation, that can't happen. These two parts are being pulled in the same direction by the same force. Okay? That force is going to be distributed to both of them. All right? Everybody okay with that? Okay? So the most important thing about a system is all parts accelerate at the same rate. Okay. All right. So we have two identical blocks, or two blocks made, sorry, of identical material. Obviously, they're different masses, connected by a light rope on a level surface. An applied force of 55 newtons causes the blocks to accelerate. While in motion, the magnitude of the force of friction on the block system is 44.1 newtons. Calculate the acceleration of the blocks. Okay, so here's what we know. there's a force here of 55 newtons. There's a force of friction acting on the block system of 44.1 newtons. What should I do to this diagram right now before I do anything else? Those masses, are they moving together? How much mass is the hand pulling? Right. This is really what's going on. Agreed? That's what's happening here. Okay. It's a system. All of that mass is being pulled at the same time. Now, there are going to be questions where the items are going to be separated, and we'll have to find individual forces within the system. But for right now, this is what's happening. The whole system, all 30 kilograms, is moving together because of a 55 Newton force this way and a 44.1 Newton force this way. Right? So what we have is we can calculate our net force on the whole system. Okay? That net force on the whole system is going to be 55 minus 44.1, or 10.9 newtons. Okay? I want to calculate the acceleration. F net equals mass times acceleration. I just calculated what F net is. How much mass is being accelerated here? 30 kilograms. There's another thing about systems. Whenever we're calculating something about the whole system, we use the whole mass of the system. Sometimes questions will try to trick you. Okay? If I was asking this question, I'd be trying to trick you, obviously. Okay? I wouldn't say calculate the acceleration of the blocks. I'd say calculate the acceleration of the 10 kilogram block. And what would people do? They divide this number here by 10 instead of 30. The whole system is accelerating, not just the 10 kilogram block. I calculate the acceleration of the 10 kilogram block by calculating the acceleration of the whole system. The whole system accelerates together. Okay, that's what we have to remember about systems. They accelerate together. Okay, so the acceleration is going to be F net divided by m. That's 10.9 divided by 30 kilograms. All right, so the acceleration of that system is 0.36 meters per second squared forward. Okay, everybody all right with that idea? Right. It becomes a bit more complex when they start giving us pieces of individual information. Did they say right? Yeah. Okay, yes, then it should be right, not forward. Right fits better. Okay, so what could happen and what's going to happen next is the question is going to start separating the system. And it's going to say things like, find the tension in the light rope that's connecting the two boxes. Okay? Now, in order to do that, it's got to give you individual information about the boxes, like maybe how much friction is acting on just this box or just that box. And then you have to kind of work around the whole system. But you get to keep this piece of information. That piece of information applies to the whole system and thus to both parts of it. So regardless of what they ask me to find next, I know the acceleration of each box and both boxes is 0.36 meters per second squared. Yep. Okay, is everyone all right with that? Okay. So, I want you guys to try question 2 first, because it involves these two boxes, okay? So the stuff we were working on before, okay? So 10 kilogram block, magnitude of 14.7 newtons, okay? Is the friction that's acting on just the 10 kilogram block, okay? So what we're gonna have to do here is now break the system apart and deal with it individually, okay? Think about what forces are acting on the 10 kilogram block. right? Because they want you to calculate the tension in this cable right here, or that rope, okay? This part don't do. You already know that. It's 55. I don't know why they asked you to calculate that. They gave it to you. The tension here is 55. They told you that in the question. Okay? All right, I'm going to give you a few minutes to think about that one. All right, it's a little bit tricky. Okay. Anybody want a hint? Okay. You're going to solve for this. You can solve for it using either box, but my suggestion would be solve for that tension that's between the two boxes using the first 10 kilogram box. Okay, draw a free body diagram that shows the three forces acting on the 10 kilogram box. So, as I said, there's a way to solve this using either box. But right now, you have more information about the 10 kilogram box. Okay? And what I mean by that is, if I draw a free body diagram of the 10 kilogram box, I can easily identify the three forces that are acting on it and know their values. Well, except for one of them, because that's the one I have to find. Okay? So, here's my 10 kilogram box. It's being pulled this way by 55 newtons worth of force. Okay? We know that the force of friction acting on it is 14.7 newtons. What's the other force acting on the 10 kilogram box? The tension in the rope from the 20 kilogram box. I mean, think about it. If I just walk, that's easy. I only have to overcome friction. But if I'm pulling a wagon behind me, it's harder to walk because it's pulling backwards on me. Okay? That's why it's harder to tow a trailer than it is to just drive without a trailer. The trailer pulls back on you. It resists you. Okay? So, I have this other force, and that's the one I'm looking for. The tensional force in the rope that connects the two boxes. All right. So, if I'm writing out my vector sum of all forces, okay, I know that I've got tension plus the force of friction plus the applied force. Okay? This is my applied force. This is my force of friction, and that's my tension. Everybody okay with my vector sum of all forces? Okay. I'm trying to find this force. I know this one, force of friction. I know this one, force applied. Do I know the net force? don't, but can I get it? How? Mass times acceleration. Remember, in the last question, we calculated the acceleration of the system to be 0.36 meters per second squared. So I can calculate the net force acting on the 10 kilogram block. That's what I need. It'll be the vector sum of all the forces acting on the 10 kilogram block. Okay, so my net force is 10 kilograms times 0.36, which is 3.6. Okay, so now I know 3 out of the 4 forces, which means I can solve for the one I don't have, the tension in the rope connecting the two boxes. Okay, so this is what I meant by you can apply that to individual parts of the system if you want. It applies to everything, the whole system and the individual parts. Okay, so I'm going to take F net, and I'm going to subtract the force of friction and subtract the applied force, and that's going to leave me with the tension. Right? So what that's going to look like is this. 3.6 newtons forwards minus negative 14.7 newtons, because that's friction and it's backwards, okay, minus 55 newtons. That's the forward force. Okay? That's going to equal my tension. All right, so when I do that, I'm going to have 3.6 plus 14.7, because it's minus negative, right? And then minus 55. All right, so my overall force resisting me from the 20 kilogram box is 36.7 newtons, okay, in the negative direction. Everybody all right with that? Yeah? So that was one way to solve that. Sorry, everyone okay with that? Here's the other way to solve it. I can use the 20 kilogram box to solve this as well. Here's how. They told me in the first question that the total amount of friction on the whole system was 44.1 newtons. Then in this question, they told me that 14.7 of that is acting on the 10 kilogram box, which means whatever's left is what's acting on the last box. Everybody okay with that? Okay, so if I do that, okay, so 44.1 minus 14.7, okay, 29.4. All right, so I've got, on the 20 kilogram box, the force of friction is 29.4 newtons. That's the tensional force. Okay? The rope that connects the two boxes is the force that pulls forward on the 20 kilogram box. It pulls backwards on the 10 kilogram box. Everyone okay with that? Okay, so I've got a free body diagram drawn for this. Now, I can say the sum of all forces on the 20 kilogram block are the tension plus the force of friction. Can I calculate the net force acting on this box? Okay, take my acceleration, 0.36, multiplied by the mass, 20, I'm going to get 0.72, or sorry, 7.2 newtons. Everybody okay with that? So now I can calculate my tension. Tension will be 7.2 minus negative 29.4. Okay, that's going to be 36.7 newtons forward. Same as we got for the last. Okay, so more than one way to skin a cat. Why you need to skin a cat, I don't know. But apparently there's more than one way. All right, so that's a system question. The big thing to remember about systems is that all the parts of the system accelerate at the same rates. Okay? Sometimes you're asked about the whole system, sometimes you're asked about individual parts, okay? But we don't do anything really different. We draw the free body diagram, we set up sum of all forces, and we go from there. All right, I want you guys to try question number 1 about the buckets of nails. Okay? It's similar to the 2 blocks being pulled, except it's vertical. It's an elevator with 2 cars, okay? 2 buckets. See if you can figure that one out. Okay, draw it out, give it a try. It works a lot like this one did. Okay, so even though, like, the last question there where we broke that system up into parts, like, was there anything really mathematically difficult about what we did? We did some addition and subtraction, we did some multiplication and division, and that's it. There isn't anything ever that's mathematically difficult about Newton's second law. Newton's second law is conceptually difficult. We have to really be able to visualize what's happening, okay, in order to isolate forces acting on parts of a system or object. Okay, so for this first one, okay, where we have the two buckets, so we got this bucket of nails connected to this bucket of nails, and then a force acting directly on the first bucket. Okay, each bucket is 5 kilograms. All right, tension in the rope connecting the buckets is 60 newtons. All right, so the tension in this is 60 newtons. Right? What's the other force acting on that bottom bucket? Gravity. Okay. Could I calculate what the force of gravity is on this bucket? Yeah, 5 times 9.81. Everyone okay with that? Right, so that's going to be 49.05 newtons. Okay, so they want us to calculate the acceleration of the buckets. Now, I can't calculate the acceleration of the system as a whole because I don't know what this upward pulling force on the top bucket is. But if I remember that all parts of a system accelerate in unison, I can realize that if I can calculate the acceleration of any part of the system, I have the acceleration of the whole system, which is what they want. So if I'm looking at what I have right now, I can calculate the net force acting on the bottom bucket. Agreed? I know how much is pulling up, I know how much is pulling down, and I know the mass of that bucket. So I can calculate the acceleration of that bucket and thus the entire system. Okay? So that's what I'm going to do. Okay? I'm going to say that the net force on the bottom bucket is the 60 newtons plus negative 49.05. So we're going to be looking at 10.95 newtons is our net force. Okay, that equals mass times acceleration. Only thing I have to remember here is I'm only doing this for which bucket? One of them. So I don't use 10 kilograms here, I use 5. Okay, so I take this, divide both sides by mass, okay, and I'm going to have the acceleration, which is going to be 2.2 meters per second squared up. That's for both buckets, or each bucket individually, because they are attached. They are a system. Okay? They will accelerate together. Okay, it's a lot to digest today. Okay? And we're not even a quarter of the way into it yet. It gets even more interesting when we start talking about pulleys, which change the direction of forces in a system. Still system, still works the same, but we changed the direction of forces. All right. Sorry, Carter, I think I walked right in the middle of your picture there. Okay. All right, we'll let it go for there for today. Okay, I'm going to come around and spray down your desks. Okay. And then we'll head out.